Hi, welcome back to this video series on Diffie-Hellman key agreement algorithm that we have been talking about for quite some time. Today I will focus on the final phase of key exchange where both Alice and Bob derive, for example, an AES key from the shared secret. So in particular, my focus is on this. Let me quickly show you um, the final phase, okay? This is the final phase, right? When both Alice and Bob exchanged their public keys, right? For example, Alice's public key A is sent to Bob and vice versa. Bob's public key is sent to Alice. How are they arriving at the shared secret? Alice takes Bob's public key, writes it to her private key X, right? All in modular arithmetic, of course. We are working here in ZP star. Similarly, the Bob side takes Alice's public key, writes it to his private key. Everything that you see in red is private, and blue is public. Okay, so we have discussed in the past that why both sides will end up with the same key k. It's just a simple mathematical rule of exponentiation. So one question is now that they both have the same secret, can they just use it directly to for example, to encrypt something using AES, advanced encryption system, right, or standard? It turned out that that is not a good idea. The reason is that AES expects a random key. So why not use the key k as a random key? The key k that you're seeing here, it is not really random in the sense that what you get here is a group element, right? The key k is a group element, okay? It's not a random element in the AES sense, right? It's not an AES random key that we can plug it in. I'm going to show you an example, what I mean by a random group element. So we don't want to directly use the shared secret to do encryption. You don't want to chop the first 256 bits, for example, if your goal is to produce an AES 256 bit key. So there is a NIST standard for how to convert shared secrets into an encryption key or a MAC key or whatnot. So I will briefly show that standard. There is some value in using that standard to avoid this problem, in the sense that the secret key that you're seeing here has a mathematical structure, right? It's coming from b power x mod b. So of course the attacker sees A, attacker sees B, because they are publicly exchanged, but it's difficult, as far as we know, it's difficult to find X or Y from the public data. So it's still a complex problem, but nevertheless, the key has a mathematical structure, okay? So we want to avoid mathematical structure. We want a random element. Therefore, we need to apply key derivation function. Okay, let's get an example and explain why this idea of directly using the key k is not good first, okay? So what I'm going to do is I'm going to take a simple group like Z star 11, right? And I will try this now quickly. Z star 11 is a safe prime because we can write P equal to 2 times Q plus 1, right? So we can do that happily. So what I'm going to do is I'll just select a group element as a generator. What is the generator? A generator is something that generates a group that you wanted to work with. So what if I took my group element G equal to 3 as a generator, okay? So what type of group G equal to 3 will generate? Okay, we talked about groups and generators in the past videos, so I will quickly run this. When we take G equal to 3, if you look at this table, G equal to 3 occurs as part of the second column, right? That means 5 power 2, for example, 5 power 2 in mod 11, right, is 3, or 6 power 2 in mod 11 is also 3. That means 3 is a quadratic residue, right? So if you have a quadratic residue as a generator, which means it's going to generate all other numbers that can be written as power of 2. So what are the numbers that can be written as power of 2? Naturally, every element that you're seeing as part of the column number 2, right, 4, 9, 5, 3, 1 are all quadratic residue. So what I'm arguing now is that the key that you will get when Alice and Bob exchange the public keys and then apply the math, the shared secret they're going to get will be an element. What are the elements? It can be either 4, 9, 5, 3, 1, because these are the elements of column number 2. Basically the shared key will get stuck here. Okay, this will be one of the shared key elements. Okay, so the shared secret is in that set, is in the above set. Okay, so naturally this is not a uniform key. If you select a uniform key in the AES sense, you will not have a mathematical structure like this. Here I clearly say that this is going to be the key. The key can be the 4, 9, 5, 3, 1. Of course, if your group is much larger, you have a larger set, but still the mathematical structure is preserved, right? The key is going to come from column number 2. That's for sure, independent of how many bits your key size is. It doesn't matter it's 2048 bit or 4096 or whatever. Okay, it's going to be as part of the column number 2 if you use safe prime. Okay, column number 2 of this table that we have been talking about for quite some time. So let's run this simple scenario now with a simple example. What I'm going to do is take my P to be 11, right? G to be 3. Let's run this example as Alice first. What is Alice going to do? She's going to pick a random number X, which is her private key. Let's take X to be 7, right? Alice's private key. And then Bob does something similar. Let's just say he picks, it has to be random, but I'm just picking for a demo anyways. Okay, so both of the participants have private keys. Now Alice is going to compute the public key by doing G power X mod P, and the same thing Bob will do. He's going to compute G power Y mod P, and then Alice and Bob exchange the A and B. So now consider how Alice is going to derive the shared secret. Okay, let me call it a shared secret, right? Let me show you Alice, right? How is she going to compute the shared secret? She takes the public key from Bob and writes it to her private key, right? And what about Bob? Bob takes Alice's public key, writes it to his private key, right? That's how Bob is going to compute his secret. Okay, and now we expect that these two secrets are the same, better be the same, because that's how we argued earlier that, okay, this is 1 and this is 1. Okay, we got the shared secret, which is the same in both cases. What can we do now with the shared secret? The shared secret is agreeing. That's good. Okay, we argued earlier the shared secret will be used to convert it into an encryption key or a MAC key or whatever. And now, as I have pointed out, the value 1 is actually clearly sitting as part of column number 2, right? It has 4, 5, 3, 1. Okay, so why not we take different X and Y and see what happens? This is of course true for any X and Y that they pick, but that's okay. Anyway, we can leave it here. So we have seen that the key is clearly an element of column number 2. That's observed. Okay, so what is the big deal if we just use that as the AES key? Just, for example, take the first 256 bits. I mean, this is a small group, you don't even have 256 bits, but I will just blow this up into a large group in a moment. So why not I just do it right away? So I'll just go here, right? I will show you an example with the 256-bit key. First, I will do a simple demo on RFC 791 data set. Okay, here you have PQG. We have been using this same data set for quite some time. What I'm going to do is just copy this, right? And I will be generating some Diffie-Hellman keys, and Diffie-Hellman protocol. I will run that and then show you the shared secret, and then I will show you how you could use the the idea of a key derivation function. Okay, so what I'm going to directly do is just go into my demo code, right? This is I'm going to comment some parts because this is the part I would like to spend some time later applying HDF to the key. What I will just do though is just quickly do this. It's a bit of a hack, but it's fine. Okay, I'll just comment this. I will compile this code and use the really large data set. So the data set I have is naturally published online from RFC. So you have B, Q, and G. What I'm going to do is just run this on my demo code. This is my own little demo code, right? So it requires P, Q, G. So Java demo. Okay, I'm going to do P, Q, and G, and it requires a fourth argument. What is the size of the exponent? Remember, Alice and Bob, they picked an exponent X and Y, and you can choose it. I'm going to choose, say, for example, a 256-bit exponent, okay? Just to speed up the execution process. Okay, so what happens now? Perfect. I have my P and Q with an X in the front, which Java's big integer doesn't like. So I'll have to remove that. Right. So I will remove the 0x. The same with my Q, I believe. I have the 0x, so I have to remove that. And now hopefully, let me clear the mess. And let's see what happens now. Okay, so now the Diffie-Hellman protocol is running between Alice and Bob. And I wanted to just zoom into a few things quickly. So here's the shared secret, which is a large number as a result of the Diffie-Hellman key exchange, because I'm playing with a 2048-bit group, right? So it's a really huge and shared secret anyways. But I added an extra test to demonstrate to you that the shared secret is indeed an element of the subgroup. Okay, so as you can see, shared secret is subgroup element. Yes. How did I detect that? Okay, well, very simple. I will just show you what I did there very quickly. So remember, the structure of the group that we are dealing with is P equal to 2Q plus 1. These are enormous large numbers, 2048-bit. P and Q are both primes. P is 2048 and Q is about 2047-bit, large numbers, right? And how did I check the shared secret which Alice and Bob have is part of the subgroup of order Q. Okay, this is all group theory that we discussed earlier. The shared secret is an element of the subgroup of order Q. Okay, this is a cyclic subgroup. Okay, so we can check it very quickly. How? All we have to do is take the shared secret. Let's call it K for a moment. We raise it to power Q, right? All in mod P. What is Q? Q is nothing but P minus 1 by 2, right? So we have K is equal to K power Q, which is Q is equal to P minus 1 by 2. And I just checked whether this K power P minus 1 by 2 is 1 or not. Okay. If it is 1, I know that K is a quadratic residue. So it's part of the quadratic residue setup that we talked about earlier, according to Euler's criterion, right? So is this 1? If it is, then you know K is an element of order Q. K can also be a generator, actually, because we are still working in the same subgroup of order Q. Okay, so that's what I did, and I will show you in the program how I just quickly check that. Okay, so now we can go to the demo code. And what did I do? So I just did the same thing. I took the shared secret, right? Both Alice and Bob have the shared secret. I raised it to the power of Q, and I checked whether it's equal to 1. It turned out to be the true. That's why you're saying true there. Okay, so shared secret is although a large number looks random from outside, it has some nice mathematical structure. It's an element of a subgroup of order Q. Okay, so we don't want to have the kind of structure and not use AES directly like that. So I wanted to show you an important research findings from um, one of the inventors of the hash key derivation function, HKDF, right? From IBM, Hugo, I don't remember his family name, but anyway. So this picture shows what I was trying to tell you. So here is the big ball group we are working with, 2048-bit. But my subgroup was not of order 2 power 256. I had p equal to 2q plus 1. Here he has a subgroup of 256. So I'm going to select a subgroup now, a different subgroup from a different RFC. Okay. So here is the ZP star group, but instead of p equal to 2q plus 1, here we have a different structure. P is equal to some large number j times q plus 1. Okay. So this is basically the structure of this group that I'm going to play with now. Okay, when I say I'm going to play with it, I mean something like this. So p is equal to some j, which is an even number, of course, otherwise the p won't be prime. So this is the structure. They gave p and q. P and q both are primes, right? Are both primes. So the question now is, what type of element the shared secret will be? What is the group the shared secret will sit in? Okay. I argue that the shared secret will sit in the group of order q. Okay, shared secret is an element of order q. Okay, so in this example, what is the size of order the group of order q? In this example, q is a 256-bit number. Therefore, the subgroup that the shared key will sit in is of order 256-bit. Okay, it doesn't mean the shared secret itself will be 256-bit. Okay, that's something sometimes confusing. The subgroup can have elements which have more than 256-bit elements. That's not a problem. But the number of elements in that subgroup is 256-bit. Okay, so meaning there are 2 power 256 possible elements in that subgroup. Okay, which is much smaller if you consider the original subgroup, right? The original group itself is made of 2048-bit. That means 2 power 2048 elements, but we are going to only work in a small subgroups. That's not at all uniform, right? In the context of 2048-bit, if you compare it against 256, it's a small subgroup. Okay, and therefore key derivation functions will actually transform this into somewhat uniform random element. Okay, that's what I'm going to show you. Okay, so let's dive into the demo directly. Let's take it to the demo now. Okay, what I'm going to do is just take the example here and apply it on RFC 5114, right? That's the RFC I would like to show you now. So this is the RFC that I show from the publication. This is the data from the publication. So let's clear this just to make it more clear. Okay, so we have PQJ. Everything is ready now. We can just run this thing. J is implicit, right? We can derive J from P and Q. Okay, so let's run this thing quickly. So here it is. I'm going to run this. It should be much quicker now because we're working with a subgroup. Okay, so what it is showing is the shared secret is also, of course, in the subgroup. Okay, and it is this large number. This is not 256-bit, as I said, but it is coming from a subgroup of order 256. Okay, 256-bit. So what is the point I'm trying to say? The point I'm trying to say is that the shared secret has some structure. It's not a random element in a broader sense. Okay. Okay. So what shall we do now? We can do some simple things with the HKDF, which is the hashed key derivation function the NIST and the researchers have published. So what I'm going to do is I'm not going to apply HKDF in a very precise and correct way. That's not my main intention. However, what I'm going to do is I will take the shared secret that Bob and Alice have. I will call my HKDF function, which I demonstrated in other videos, how HKDF works, which basically takes the shared secret, right, which is the shared secret here, and converts the shared secret into a random number. Okay, basically it extracts randomness from the shared secret, which has some randomness. It's not easy to predict, of course. It's still a lot of complexity to predict, but it's not uniform. So HKDF is kind of random extraction in quote unquote, And it is using something called salt because I'm going to use the NIST standard for key derivation. This is published very recently by NIST. There are two different ways of converting. Actually, there are three ways now. Converting your shared secret into an AES key. For example, I'm going to pick one. What I'm going to do is I'm going to use this figure one, which I actually briefly talked about earlier in the HKDF session. So my salt is going to be simple salt at this point. It's not going to be fancy like the way they explained it in NIST article, that for Diffie-Hellman key exchange salt, there are multiple rules for how to initialize the salt. I'm going to take a simple approach, just initialize the salt to be 0, which is again not very bad, but not good either. So usually preparing the salt means you can combine, Alice and Bob can combine the public keys to come up with the salt. And there are other things like nonce and so on, but at this point it's okay to use a 0 as a simple salt, okay, which is perfectly fine in many cases. I wouldn't do it in a production like code, but this is okay for a simple demo. Okay, so the point I wanted to get across though is that now after we apply say the HKDF, I would like to show to you that the shared secret is, after you transform the shared secret, the new element is actually not going to be always stuck in the small group. What I mean by the stuck in the small group is this, that here the point G power XY is the shared secret, right? It is not going to be always sitting in this subgroup. It's going to jump out after you do the transformation. The HKDF is actually doing the transformation for us, okay? So let's see whether that's true. So I'm going to do something really silly. Before constructing a 256-bit AES key, I decided that I will just take the shared secret, excuse me, and I will transform the shared secret into another secret exactly of the same length. Okay, so usually you would not put shared secret dot length. Here you will put 256-bit if you want a 256-bit AES key. But I'm not going to do that. I'm going to create another key which will be exactly the same length as the shared secret, but I wanted to show you something different, right? I want to show you that that new key is actually not necessarily part of the subgroup of order Q. That's the part I wrote it here. Okay, so I have this key that I got from the HKDF, but I wanted to argue that that key may not be an element of the subgroup of order Q. Okay, so let's try that. Let me compile the code again. Here it is. You see here, after applying HKDF, of course, this is not at all an AES key, although my program prints in a prefix AES key. So here is the shared secret after transformation, right? The original shared secret both Alice and Bob have is this, and that gets transformed into a new shared secret. But I checked whether this new secret is still an element of this little group. Answer is no. You see here, it's false. Okay, it's not sitting in that little group. Okay, it is going out. So let's try a couple of more times. Yeah, it's still false. So as you have seen now, HKDF basically transforms your shared secret into another element, which is not really a quadratic residue. That's basically it. Okay, so now let me show you, now that I ran 3 times, let me show you how you would derive a proper AES key. Okay, so again, with an exception of the salt being somewhat imprecise, but salt being 0 is not totally a ridiculous thing to do. If you can have a random number, which need not be secret, by the way, salt need not be secret. I talked about HKDF in other sessions. You can use a nonce if both the client and server or Bob and Alice have an authenticated nonce, they can use that, or they can use both others' public key to come up with a random number, which is basically a good salt. And then a context is something that is sort of a metadata, if you want to say like that, associate with the particular key. Okay, so for example, an IP address, or not necessarily IP address, because IP address will be different between the machines. Something unique for that particular communication. Okay, maybe some kind of a metadata. Okay, that's basically the context. Context is a string. Here I have a simple string, demo context. It's not secret, you can hard code it. Okay, but it has to be unique for each communication, right? Otherwise, why do we need the context? We need the context just to make sure that two different machines don't have the same key. Okay? The context will make sure that HKDF produces a random number, right? That's basically it. And you can also leave it to empty if you think that's not necessary. Okay. All right. So we have the salt on a context. So let's just now produce a simple AES key. Instead of this enormous key, we will produce an AES key, which is 32 bytes, means 256 bits. So usually salt is not necessarily secret. You can keep it open, but it has to be random. I am keeping a salt to be 0, okay, for demo purposes. But in the NIST standard, there are guidelines of how to establish the salt when you are using DH protocol. And the context is also something that helps you to identify this particular application-to-application communication. Okay, so I'm not so precise about salt and context, by the way. You have to look at my other videos on HKDF. But what is the point of this demo now is to show you how we can get a uniform 256-bit key. Okay, so here is the uniform 256-bit key. If you count the number of hex digits, let me do that using computer. Echo minus not include the new line. It should tell me 64 characters. That means there are 32 bytes. Each byte multiply by 8 to get 256 bits. Okay, so you have it now. All I did is basically apply the traditional DH protocol, and then I converted the shared secret into another secret using the HKDF function, right? This is basically the conversion part. Why do we do that? We do that because we want to destroy the mathematical structure built in the shared secret. And I have demonstrated to you that applying KDF destroys that structure, okay? And by the way, the NIST also allows you to specify other algorithms. For example, here I use the HMAC algorithm to transform my shared secret into another secret. You could use KMAC, which is the SHA-3 based MAC algorithm, KCHAC based. That's also another possibility. And what is the main concluding point is that using the shared secret directly by, for example, taking the first 32 bytes or the last 32 bytes is not a good idea, because you're still going to retain the mathematical structure. Now we think the HMAC functions behave like a random function. There is some kind of a belief that it is like a PRF, and there are some proofs, okay, as long as the compression function is a BRF, pseudo-random function. HMAC is also behaving like a PRF. PRF means pseudo-random function. So the belief is that there are no mathematical structures like what you saw in the Diffie-Hellman key exchange, okay. All right, so basically that's all. Be careful about the salt and context. It's not exactly applicable everywhere. This is something okay for my demo purpose. For this purpose, this is perfectly okay. All I did was basically take the shared secret and transform it into another secret using the HKDF function, which I talked about in the other video. Okay, that's basically it. And thank you very much for your attention.